This chapter name is stress. So here we try to understand about the stress and its caution and confusion and other questions. So let's begin. The previous chapter we looked at how strain can be observed and measured in deformed rocks. The closely related concept of stress is much more abstract concept, as it can be never be observed directly. We have to use observation of strain to say something about stress. In the other words, the deformation structures that we observe tell us something about the stress field that the rock experienced. The rotation is not straightforward, and not even the most precise knowledge of the state of stress can be predicted. The resulting deformation structures unless additional information such as the mechanical or physical properties of rock, temperature, pressure, and physical boundary condition is added. The most basic concepts of stress are presented here before taking at stress at the lithosphere and the relations between stress, strain, and physical properties in the following two chapters. So here here we are discussing about its definition, magnitude, and units. So the term pressure and stress is more often interchangeably, but structural geologists we need to use this term more carefully. In geology, use of them pressure is generally limited to media with no or very low shear resistance, while stress is used when dealing with the media with a shear resistance. To check if the medium has a shear resistance, put some of it between your hand and move them parallel but opposite direction. The resistance you feel reflects the shear resistance. Water will have no shear resistance, while clay and loose sand will have resist shearing. Okay, that's a great thing, great example. Here is in a bodied porous sandstone layer, we can talk about the both pressure and stress. It had the certain pore pressure and it is certain state of stress. They are both related to the external forces that affected the rock volume. There are two different type of forces. One type affect the entire volume of a rock. The other side as well inside is known as body forces. Body forces define three-dimensional fields. The most important type of body force in structural geology is gravity. Additional example is magnetic forces. The other the other type of force act on surface only and it is refers to as a surface forces. Surface forces originate when a body pushes or pulls another body. The force that acts across the contact area between two bodies that is surface. Surface forces are the great important during the formation of rock. In a similar way, we can talk about stress on a surface and state the stress at a point. Stress on a plate is vector quantity, while stress in a point in the second order tensor. So here we are we are talking about important point. Stress on a surface is a vector, while stress at a point is second order tensor. Engineers and rock mechanics oriented geologists may refer to stress on a surface interaction and reverse them the stress to mean the state of stress at a point in a body. Also, as geologists, we need to aware of these two different uses and avoid confusion between those meaning of the stress. So next thing is here is stress on a surface. The stress on a surface such as the fracture or grain contact is a vector that can be defined as ratio between force and area across which the force act stress that act on a point on surface can be formed as sigma limit delta F by delta A. This formation indicates that the stress value may change from place to place on surface. The SI unit of force is Newton, means mg kg per second square, means 1 Newton. Force that surface on earth that is created by mass of 100 or 2 kg, 100 or 2 gram. Some geologists use may unit dyne, watt dyne, centimeter 10 to 5 Newton. Different stress pressure given magnitude MPa where 1 PA 1 Pascal means 1 Newton into meter square. Newton meter square, 1 megapascal means 10 var and 10 to power 19 kb centimeter cube 145 centimeter and 100 MPa equal to 1 kilowatt. Okay. Compressive stress are normally considered positive in geologic literature. Compressive stress are normally considered positive in the geologic literature, while tensor is regarded as negative. In material science, the definition is reserved so that tension become positive. This, this is related to fact that the tensile strength of material is lower than this compressive strength. Tension strength become more important during the elevation of construction such as bridges and buildings. The crust, on the other hand, is dominated by compression. Remember the difference between stress and strain. Both tension and construction can be result from stress field. All the stress area are compressional. Okay. Next thing here is the stress in lithosphere. Stresses in lithosphere are mostly everywhere. Compressional, even the rift and other undergoing extension. Normal stress and shear stress. What is normal stress? What is shear stress? Okay. The stress vector oriented perpendicular to a surface is called normal stress on that surface. While the stress vector that act parallel to the surface is referred to the shear stress. In general, stress vector act obliquely on the plane and the stress vector can then be resolved into normal and shear stress component. It is emphasized that the concept of normal and shear stress has a meaning only when related to the specific surface. Well, the decomposition of surface is quite simple. The decomposition of stress vector is slightly more complicated. The complications related to the fact that stress depend upon the area across where they are acting while the force do not. Therefore, the simple vector additional does not work for stress vector. So figure 4.1 is we have the relationship. Here they are showing the signs of conversion. Compressive normal force is always positive in geology, while the tensor are one is negative in engineering geology. To shine convection and the opposite. Geologists like the convection because stress tends to be compressive in the crust. Note, however, the shear stress are subjected to least convection. For the Mohr circle construction, we have the following convection shear stress constant while the clockwise rotation is negative. For the tensor rotation for sine convection, the difference for the shear stress absolutely valuable identical. If the shear components on the negative hidden side to recur in showing figure the x positive direction for the coordinate axis, then the sign positive, the vice versa. This may be confusing, so always check the sign the opposite circulation makes sense. Okay, so see here is a more convection, more convection and more convection. This is a showing this is a positive, this is a negative. Why positive is compressional, is positive and tensional is negative. Here is the showing negative, here is the positive. Okay, so here is the positive and here is the negative. Okay, so here is the positive and this is the negative. Okay, that's it. That's the good concept. Okay, so here is some mathematical expression of sigma and normal sigma, normal shear and normal stress and shear stress. Okay, well, the theta is the angle between the stress vectors and the surface of caution or the dip of the surface. If the stress vector is particle for compression, the decomposition of vectors into the normal and shear vectors given Fn equal to F cos theta and force for shear stress is F sin theta. These four function is illustrated graphically in the figure 4.2. Okay. So next chapter is stress at a point. We leave the concept of stress on a single plane to consider the stress of a stress at a given point in a rock. For example, a point within the mineral grain. We may imagine that plans in infinite number of orientations through this point. Perpendicularly across each of plane, these are two opposite directions and equal long traction or stress vector. Different pair of stress vector may different length and when a representative family of such vector is drawn about the point and ellipse emerges in two-dimensional figure 4.3 and the ellipsoid is defined in three-dimensional figure 4.4 and obvious reminiscent for expression stress and ellipse that is not complement the positive and negative traction, and the ellipse is called the stress ellipse and the ellipsoid is called stress ellipsoid. So the stress ellipsoid and its orientation tell us everything about the state of stress at a given point on in a rock or in a rock volume in such stress is homogeneous. So here is the figure 4.4.1. It shows the vector force F acting on a surface can be decomposed on a normal and shear component. Why simple vector additional? The stress vector sigma cannot be decomposed in view because depend upon area of across the force acts. The trigonometric expression for the components sigma and sigma s are derived. So here is sigma n sigma s, this sigma fn equal to f cos theta, sigma s equal to f sin theta. Okay, f sin theta and cos theta. So here is force is acting, here is sigma normal force is working here, and the force of shear force is working in that direction. Okay, so here are the some relations for the this is the okay force is working and stress is F by A. Okay, so there is no confusion about this. A simple diagram is showing the stresses. Okay, so next thing our here is the stress ellipsoid. The stress ellipsoid has three axes denoted sigma 1, sigma 2 and sigma 3. The longest sigma 1 is directional maximum stress, where the shortest is known imaginary plane across the valve, the last fraction than the across the another plane through the point. The axis is called the principal stress, and there the post is the principal plane of stress. These are the only plane where the shear stress is zero. The stress component, next is stress component. The the state of stress at a point is also defined by the stress components. They act on the of each of the three original surface. The infinite cubes, each of these surface has a normal stress vector sigma and the shear sigma s along the two edges. Illustrated in figure 4.5 in the total, this is given the three normal stress vector and the shear stress vector. If the cube as the rest is stable, the force act opposite directions of equal. Okay, so here we are seeing some graphical representation of force. Like the first figure shows the normal component of force Fn and stress Sn vectors acting on the surface, plotted as a function of the orientation of the vectors relative to the surface theta, and see the figure 4.1. Note the difference between the two. The sum of the B option B, the sum for the shear components. Note that the shear stress as the maximum at 45 at the surface, while the maximum surface at the obtained parallel to the surface. Okay, so here's the Fn is 45, as Fn is sigma. Here is the 100%. This is going to down to here and down to fall to here. So the magnitude and hence they cancel each other out. Of this implies that sigma x by equal to minus by x, sigma by x minus z by sigma xz minus sigma zx, and we left with 6 independent stress component. The cube can be oriented so all the shear stress are zero. Whereas the case the non-zero components at the three normal stress vector. In the situation, the vector represent the principal stress directional, that is principal stress principal axis, or principal axis of the stress ellipsoid. The three surface is defined axis, the principal stress, then we define ellipses, right, and the 3 into 3. The two-dimensional illustration of stress at a point three planes A, B, and C are oriented perpendicular to the section in the quotient, and the normal stress are represented in the form of vector corresponding colors. The stress vector define ellipses whose elliptical depends on the state of stress. Next we have topic is the stress tensor or matrix. It is used to put the 9 component of stress into the maximum. The second tensor is known as stress tensor or stress matrix. Sigma 11, sigma 12, sigma 13, sigma 21, sigma 22, sigma 23, sigma 31, sigma 32, sigma 33. The normal stress is sigma 11, sigma 12, sigma 33 occupy the diagonal, while of the diagonal representation of shear stresses. We have the sigma 11 equal to sigma xx, sigma 12 equal to mod xy, sigma 13 equal sigma etc. What may have different sign because different conventional used to tensor components. In the stable situation where the force is balanced, we have sigma 12 equal to sigma 21, sigma 31 equal to sigma 13, sigma 23 equal to sigma 32, and the stress tensor can be written as sigma 12, sigma 12, 1, sigma 11, sigma 12, sigma 13, sigma 12, sigma 22, sigma 23, sigma 13, sigma 23, sigma 33. This is now the symmetric. This is now a symmetric matrix. A What is symmetric matrix? A matrix where changing columns to rows does not change anything. Okay, but the value will change with choice of coordinate system and how orientation our little cube from figure 4.5. We are lucky to orientate our little cube coordinator with care. We have now principal stress along edges of box, which is matrix become sigma 11 0 0 0 sigma 2 2 0 0 0 sigma 3 3 equal to sigma 1 0 0 sigma 1 0 2 sigma 1 0 3. Okay, not so problem. So this is the figure is called stress ellipsoid. Stress ellipsoid sigma 1 here, sigma 2 and sigma 3. Okay, and is the stress ellipsoid ho gaya. And here is stress, the stress component acting on a face of a small cube. The positive stress component shows the corresponding stress component axis on a negative and hidden face of the cube. Sigma x, sigma y, sigma z are normal stress. These others is the stress in parallel to the edges of the cube. Okay, here next topic is box is the vectors, matrix and tensor. A scalar is a real the scalar is a real number reflecting temperature, mass, density, speed, or any other physical magnitude that has no direction. The vector has a both magnitude, length, and direction, such as force, traction, means traction, stress vector, or velocity. The matrix, a matrix is a two-dimensional array of number 3 3 or 2 is most geological applications, meaning that they have 9 or 4 components. Matrices can represent the state of stress or stress in a medium. The term tensor is in the rock mechanics applied to vectors and perpendicular matrices. We can consider the scalar tensor in order 0 vector as first order tensor and matrices and the second order tensor. Hence, for our purpose, the term matrix and second order tensor is identical. However, the tensor is the both cases is the number, the array is the matrices that can be that not tensor, such as the field of economics is an important tensor is that the independent of any chosen frame of reflection, meanings that the quantity represented by the tensor, such as the same state of stress or strain can be any point in a volume, remains the same regardless of the choice of coordinate system. Hence, the vector will have the same length for the magnitude of different coordinate systems, even those are represented by the numbers. Okay. A tensor may be defined at single point or coordination isolation points, or may be defined over circulation curriculum of a point, and thus is formed a field, a scalar field, vector field. In latter case, the elements of the tensor are the function of positive position, and tensor form is called tensor field. This is simply means that a tensor is defined at every point within a region of space of a spacetime rather than just a point on a collection of isolated points. Begin the non-zero entries. These principal stresses can now readily in an extended form of matrix that three principal stresses vector as follow: three columns sigma 1 0 0 0 sigma 2 2 0 and 0 0 sigma 3 3. In other words, the stress tensor is composed of the principal. The stress tensor is composed of three principal stress vectors. The stress tensor is composed of three principal stress vectors. In the other case, we have to find the 18 eigenvectors and the 18 values of the matrix in the principal stresses vectors and principal stresses represently. This is easily done by means of readily available component program, and important know that even if element of the stress tensor vary from choice coordinate system, 18 value tensor remain the same, that is invariant. Okay. The stress tensor represents the same state of stress, same shape and orientation of a stress ellipsoid, regardless our choice of coordinate system. Since the state of stress will vary from point to point in lithosphere, so will the stress ellipsoid and the stress tensor lead to that concept of tensor field. Hence, the complete description of the state stress and the value from the given tensor field. What is the meaning of derivative stress and mean stress? Many stress tensor can be split into the symmetric matrix, where the first part represent the mean stress, and the second is called derivative stress. This is not just is another boring mathematical expression, but is a very useful terms, very useful. The component allow to distinguish two different very important component of stress, which can be denoted as isomorphic and anisotropic and component and decomposition. The total stress tensor is sigma 11, sigma 12, sigma 13, sigma 12, sigma 122, sigma 22, sigma 2, sigma 23, sigma 13, sigma 23, sigma 33. So here is mean tensor stress, and what is the derivative stress tensor? T is sigma m 0 0 sigma m 0 sigma m 0 sigma 0 0 sigma m plus the sigma 11 minus sigma m sigma 12 sigma 13 sigma 12 sigma 22 minus sigma m sigma 23 sigma 13 sigma 23 sigma 33 minus sigma mm. This is the derivative stress tensor. So here is the here we have the question, what is these things? So the sigma m, this is denoted is called mean stress, and is the simply is arithmetic means the three principal stresses, the sigma m equal to sigma 1 3 sigma 1 plus sigma 2 plus sigma 3 by 3 is a given average measure of stress. If there is no derivative stress, so we can isotropic component there. There is no derivative stress, so that is the anisotropic component is 0 with the case of derivative stress. The tensor become the identify matrix. Then the state stress or traction is identical or any plane through the plane, regardless if the orientation of planes. Furthermore, the stress ellipsoid is the perfect sphere, sigma 1 equal to sigma 2 equal to sigma 3. This is no shear stress anyway. There is no diagonal or no diagonal straight or stress tensor, such condition is mostly reported hydrostatic stress or hydrostatic pressure, represented isotropic state of stress in ellipsoid. That means the very closely related to the static pressure that is controlled by varied depth density of overlying rock columns. We have the derivation equation in chapter 5. Derivative stress is the difference between the mean stress and the total stress. Means derivative stress equal to total minus sigma m minus sigma or total sigma m plus derivative stress. Okay. The derivative stress is that derivative stress tensor represent at an anisotropic component. The total stress and the derivative stress generally considered small than isotropic means stress. What general significance when it comes to formal geological structure in most settings? While the isotropic stress result and delization in infiltration and deflagration in anisotropic component result in the strain. The relationship between the principal stress influence what type of structure are formed. The Mohr circle and diagram. Okay. Before looking at stress state in the crustal in the next chapter, we will consider principal graphical way to representation of dealing the stress that is based on diagram refers to the Mohr diagram. In 19th century, the German engineer Mohr Otto found a particularly useful way of dealing with stress. He considered the diagram in shown figure 4.46, now known as Mohr diagram, where the horizontal and vertical axes represent the normal and the shear stresses that act on the plane through a point. The value of maximum and minimum principal stresses sigma 1 and sigma 3 is also denoted sigma 1 and sigma 2. The two-dimensional case is plotted in the horizontal axis, and the distance between the sigma 1 sigma 2 defined in the diameter of the center as sigma 1 plus sigma 3 by 2 0. The circle is called Mohr circle. The Mohr circle describes the normal and shear stress acting on a plane of all possible orientation through a point in a rock. What is Mohr circle? Mohr circle describes the normal and shear stresses acting on a plane of all possible orientation through a point in the rock. More specifically, for any given point on a circle, a normal stress and shear stress value can be read off the axis of diagram. These are the normal and shear stresses acting on a plane represented by that point. So here is the Mohr circle angle between larger Mohr circle G. Mohr circle. The theta is the angle between largest stress and a given plane. Notice there is use of double angle. 2 theta is sigma 1, sigma 2, sigma 3. Okay, sigma 1 to sigma 1, and that the angles. So how do we know the orientation of plane represented by given point on the Mohr circle? In the two-dimensional, with the sigma 1 and sigma 3 plotted in the horizontal axis, the plane represented on the circle contains sigma 2. If theta is the angle between two normal to the plane, and sigma 1, as shown in figure 4.1, the angle between the radius at the point and the circle and horizontal axis is the 2 theta. The difference between maximum and minimum point principal stress sigma 1 minus sigma 3, the diameter of the circle. This difference is called differential stress. The difference is called differential stress, an important fracture mechanics. In general, great differential stress promotes rock fracturing. In the great differential stress promotes rock fracturing. The angle theta and the angle of measured in the same sense of Mohr circle in a physical space, but the angle is a doubt in the Mohr space. Two points representing perpendicular plane is the separating y 180 degree in the Mohr diagram. This is where the principal stress in both plot in horizontal place. Another reason the principal plane have no shear stress with the fulfill only along horizontal axis. This illustration is how Mohr space differential from physical space and important to understand the connection between the two. Let us explore some more doubling the angle the Mohr mean and the any plane such as the indicated by point 13, the completely plane, the same, the identical, the point 1, and the has another complement to do the normal stress, the sensor stress, different to sign only. The maximum shear stress occurred in plane where the 2 theta equal to plus minus 90 degree, where where the angle is theta 1 is 45. The Mohr diagram used in the geological application is generally constructed so compression and positive is tensor is negative, while the opposite convectional to the engineering literature is most cases the principal stresses are positive in the lithosphere, but the always the for tensional stress the Mohr circle. The most of the left is the origin in the tensor field is all apical stress is tensile is the most unuseful case in geology. Then the entire circle is located the left of the origin. The Mohr diagram can be also used in three-dimensional where the three principal stratum is plotted along a horizontal plane. This is way can be represented three Mohr diagram in a single Mohr diagram. The number of important state of stress can be represented in the three-dimensional Mohr diagram. Source figure 0.47. So here you can see the characteristic. This figure shows the characteristics state of stress is illustrated in the Mohr diagram for 3D stress. The 3D state of stress is illustrated by mean of three circles connecting the principal stress. The larger conductor contain sigma 1 and sigma 3. The three produce and 2 point of special stress. So triaxial state of stress is a sigma 1 sigma 2 here. Triaxial state of stress. Biaxial means planar sigma 1 sigma 2 sigma 3. Okay, uniaxial is a compression sigma 1 only we have only one value sigma 1. Okay, uniaxial tension. Biaxial, okay, sigma 1. Biaxial, the hydrostatic means lithostatic sigma 1 sigma 2 sigma 3. Okay, so here we have summary of this chapter. So about the summary of stress, in this chapter we have looked at the fundamental of stress. It is important to understand the difference force stress on a plane, both vector quantities, and stress at the point is a second order tensor. Stress at the point and the ellipsoid is the many way to similar to stress and the stress ellipsoid. The principal stress considered in the similar way, the principal way to principal. But despite these similarities, it is important to understand that stress is something may or may not lead to strain or force. It can be expected if the force of the strain ellipsoid is similar shape of orientation. At the point, we should be able to understand and answer the following statement and questions. The term stress can be used for stress on a plane or the state at a point, local state. The state the the term stress can be used for stress of plane or state of the term stress can be used for stress on a plane or state at a point, local state of stress. Stress acting on a plane is a vector determined by the applied force and the area of acting on. An oblique vector decomposition from normal and shear components. The stress at point describe the total stress of a stress at a point and second order tensor is three-dimensional. And the complete description of state of stress in a body is a given state and tensor field, which describe how three-dimensional state of stress in a body. The stress cannot be decomposed the same way as the force because stress is also depend upon area. Okay, so this is a few review question if you want to more understand.